In example 5, we're going to look at the probability of drawing a spade and then a club. We're going to first do it with replacement, so that means that when we draw our first card, we're going to stick it back into the deck. And then we're going to calculate it without replacement, which means that when we draw our card, we're going to put it aside, toss it to the side, and then calculate the probability of the next event, given that that card has been removed. So, first thing we're going to look at is the probability of drawing a spade, then a club. So I've got my deck of cards here. I'm going to draw a spade, and then I'm going to stick it back into the deck, and then I'm going to draw a club. So that's what we're going to do first. Drawing a spade, and then a club, given that we're going to put that card back into the deck. Okay, so with replacement, spade, probability of getting that is 13 out of 52, because there's 13 spades and 52 cards total. The probability of getting a club is 13 out of the possible 52 cards. So we can get the probability by multiplying those together. So 13 times 13 is 169. 52 times 52 is 2704. That fraction will reduce to 1 over 16. Now up to this point, at least in the last video, I wasn't worrying about getting decimal answers, but for these, I am actually going to do that. So that this is equal to 0.0625. So we've looked at these as fractions, but probabilities being numbers from 0 to 1, it's kind of easier to see which one of these is bigger than the other by looking at the decimal that's from 0 to 1. Okay, so we're gonna do that for this part of the video. Without replacement then, so that means I'm going to take the deck, I'm going to draw my spade, and then I'm going to remove it from the deck, throw it aside, and then pick a club. So without replacement, it's going to be 13 out of 52 still for the spade, but then when I remove that, I've only got 51 cards left. Now I still have 13 clubs because the card I removed was a spade, so we've still got 13 clubs. So that's going to be 169 out of 2652. And that will reduce to 13 out of 204. So here you can see, this is why I'm talking about getting the decimal answers, because if we want to know which one of these is more likely to happen, well, this is approximately that. Now, so you can see that this one is slightly more likely to happen than this one. It's not so easy to see that when you've got the fractions. Okay, example 6. Probability of drawing a jack and then drawing another jack. So first with replacement. So we're going to draw a jack off the top, stick it back into the deck, shuffle it up, and then draw another jack off the top. So with replacement, we're going to have 4 jacks out of the 52. Then for the next one, we still have 4 jacks because we put it back, and we still have 52 cards because we put it back. So that's going to be 16 out of 2704, which reduces to 1 out of 169, which is approximately 0.006. Then without replacement, so that means we're going to take our deck of cards, draw a jack off the top, and then toss it aside, and then draw another jack off of there. So we've got 4 out of the 52 for the first card, but then for the second card, we've only got 51 cards left because we took one of them out, and now we only have 3 jacks left, because when we drew that jack, we tossed it aside, and so there's 1 less jack and 1 less overall card, and so we're going to get a different answer than when we multiply this out. So that's going to be 12 out of 2652, which reduces to 1 out of 221. And again, if we get a decimal answer, just so we can compare the size of these probabilities, about 0.005. So you can see then that it is more likely to do this with replacement than without replacement. All right, examples 7 and 8 are not actually dealing with replacement, but they are things that you will see in your homework. So I want to quick run over this. So what we're going to do for this, actually I've written the formulas that are on the other side of the notes sheet here. These are the exact ones that we looked at earlier. So basically what we're going to do for this type of problem is just plug things into the formula and then solve for what we don't know. So we know the probability of event A here. We know the probability of both of them happening. So what we're trying to find here is the probability of event B. Now it doesn't matter what these events are, all we have here are numbers, but we can plug them into the formula and figure out the missing piece. So we know that the probability of event A and B is 0.2, and the probability of A is 0.25. Now we don't know the probability of event B, I'll just call that x. So we get 0.25 times x, and then we can solve this just by dividing by 0.25. And we get that x is equal to 0.8. Now again, x was the probability of b, so that tells us that the probability of b is equal to 0.8. Example 8. Exact same thing, but with dependent events. There's really no difference. You still just multiply the probabilities together. It's just that when you're calculating the probability of event b given that a has happened, that's where the tricky part is. But this is going to act just like the last one that we did. So we'd have, let's see, we know what the probability of A is, so we'll plug that in. We know what the probability of event B given that event A has happened. That's 0.5. And so to find the probability of A and B, we just multiply those together, and that's going to be 0.35.